A really important concept in simple harmonic motion is the idea of a reference circle. Now, it's not immediately obvious to see how these three pictures on the table here today are related, but I'm hoping that with a bit of thought you'll be able to see that this is just an extension of a type of scientific thinking that you're already really familiar with. So on this side here, we have our mass on our spring. And we know about real physical systems like that. We can observe them, we can understand what's happening with the forces and the energy involved, but they're not very useful when it comes to things like predictions. They're not very useful when it comes to solving problems because of their very reality. So we're already used to the idea that we can represent real physical systems in mathematical ways. And the simplest example, something that I hope you're really familiar with, is the idea that you can represent real things like a person on a bike going around a track using a mathematical system, in this case a distance time graph or a velocity time graph. That's a real physical system represented in a simplified mathematical way, because we're familiar with lines, we're familiar with gradients, we're familiar with finding areas under graphs. And all those things, all those mathematical techniques tell us things about a real system. And furthermore, they allow us to predict things about the real system and maybe to extrapolate those predictions to other real systems. And this is at the heart of a lot of scientific thinking. The idea that if we idealize a real system, we can come up with scientific ways of predicting, explaining, inventing new real systems that will do the same thing better or faster or more efficiently. And so this is a really important piece of mathematical thinking and scientific thinking. You're already pretty good at this, so let's try it with the reference circle. So we've got our pendulum here, our mass on a spring rather here, and we can say, well, if I compress the mass on the spring, if I bring it up to its highest amplitude and then let it go, it will follow simple harmonic motion. It will, of course, be slightly damped due to air resistance, but I am going to assume, for the purposes of today, that the air resistance is so small that we can ignore it for today's purposes. So I bring my mass up to its maximum amplitude position and I let it go. And I can say, well, in that case, my bob will follow this mathematical representation here. And I hope you're familiar with this. This is a sine curve. So you can see that the amplitude gets bigger, comes to a peak, passes back down through the equilibrium, goes down to its negative position and comes back up, and so on and so forth. And so as time goes on, we can predict where the mass actually is, depending on how far along it is, because sine curves are very predictable. So we're going to get to the mathematics of that in a moment. I just want you to accept the graphical representation of it for now. Let's take a look over here at this one. Now this one, it's not immediately obvious why a circle would be useful to explain simple harmonic motion. But I want you to think about this arrow, okay? And this is a type of vector. We're going to call it a phasor, okay? So this arrow here, if you can imagine at the moment, it's pointing towards the equilibrium position, isn't it? So if we drew a line all the way through there, we'd see that this is the equilibrium position. And as the mass moves up, as we move towards our maximum position, the phasor can turn in a circle until it reaches the maximum position. And then it can keep going. And when we get back to here, what have we got? Oh, we've got the equilibrium position when the mass is on its way back down. And then we keep going and we get back to, the negative position, the part where it's at its maximum amplitude, but it's at the bottom of its stroke, not the top. And then we can go even further and come back up here to our equilibrium position again. Now, this is just another visual representation of our actual real mass on a spring. It's also very, very closely related to the sine curve, even though it's not immediately obvious. It takes one period for the arrow to get back to the beginning. When the arrow's at the top, our object is at its maximum displacement. When the arrow's at the middle, on this side, it's at its equilibrium position and moving up. When the arrow's on this side, it's at its equilibrium position and it's moving down. When it's here, pointing straight down, it's at its maximum displacement and moving back up again. So the reference circle is another way of understanding how simple harmonic motion behaves. We're going to move on to mathematical understandings of these real representations of real physical systems.